Hello and welcome to our lesson on radicals and rational exponents. The rational exponents are the new piece to this topic, but I wanted to show you what happens if we have variables underneath the radical as well as whole numbers. So we know how to simplify, like a radical 32, but what if it's a radical 32x to the fourth? So luckily the process is really the same. Let me just kind of refresh for you. If we were to simplify something like a square root of 25, that's exactly 5, right? If it was a square root of something not exact, like a square root of, 28, then we're going to break this down. So 2 goes in 14 times, and then 14 becomes 2 times 7. And so we look for that pair representing a 4. Right, the 2 2's is 4, and the square root of 4 is 2, so that pair of 2's tells me a 2 can come out, and then a 7 is going to be left in the radical. Okay? It works exactly the same for variables. If we have a perfect root, like the 25, then we have this exact answer. If we have something that's imperfect, then maybe some of it will come out and some of it will stay. So for example, if it was the square root of, let's say, x squared. Now really we should know this just because of inverse operations, right? The square root and the square are opposite operations. So you should know just from that this is going to be equal to x, okay? But think about this in terms of breaking this down. Really, what is x squared? It's an x times an x. And if it's a square root, we're looking for pairs just like we were before. So the reason the square root of x squared is just x is because x times x gets you x, right? Or what if it was x to the fourth? Well, that means, what are you multiplying by itself to get x to the fourth would have to be x squared, right? That's because there are 1, 2, 3, 4 x's here. So that means there's 2 pairs, so 2 x's would come out, leaving us the x squared and nothing's left over. Now, if it's, let's say, an x to the fifth, you're not going to be able to multiply something by itself to get an x to the fifth. So if I had 1, 2, 3, 4, 5 x's in there, then I'm still going to be able to take 2 of them out, but this time I'm going to have 1 left over. So I would still have an x squared coming out, and then left over in the square root would be an x to the first. Okay, so we can do the same thing with the variables that we're doing with the numbers. However, if the variable exponent gets a little bit large, I don't know that I want to go through all of that process. So for instance, let's say we're looking at a square root of x to the 14th. Now, do I really need to write out 14 x's to see how many groups of 2 I can circle from that? I mean, I'm hoping not. Let me just show you. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. How many groups of 2 am I going to get? 1, 2, 3, 4, 5, 6, 7. If I'm breaking 14 into groups of 2, that is exactly what you're doing when you divide 14 by 2. So we don't actually have to do the writing out and the circling. Now, that's a helpful process. And if there were only 3, 4, 5, whatever x's, and you want to write them out just because there's going to be a lot of things going on sometimes in one problem, then go ahead. But if it's a larger exponent, we can just divide. We're going to take our exponent and divide by our index, and so x to the 7th is going to be our simplification. Now, if it's a square root of, let's say, x to the 15th, then there's going to be something left over. So in this case, we divide the 15 by 2, and we get 7 with a remainder of 1. So we're going to have an x to the 7th that still comes out, just like we did here, but this time we have an x to the first left over. Okay? And this will work the same if they were cubes. Or cube roots, sorry. If there was the cube root of x cubed is going to be x, because 3 divided by 3 is going to give us 1, or the cube root of x to the 6th would be x squared. And then if it was the cube root of x to the 7th, well, 7 divided by 3, let's see, it goes in twice with the remainder of 1. So we'd have an x squared still coming out, and then we would have left in the cube root an x to the first. Now again, if you wanted to just take the 7 x's, 1, 2, 3, 4, 5, 6, 7, and say here's a pair, here's a pair, here's a leftover, that's totally fine. It's just if the exponent's large, like x to the, 21st is not even that big, but I don't want to write 21 x's out. So 21 divided by 3 is going to give me x to the 7th. Okay? So let's practice putting the numbers and the variables together. We're going to simplify the coefficient by breaking it down into prime factors, just like we looked at in the previous topic. And we're going to simplify the variable piece by dividing our exponent by our index. And if there is a remainder, then the remainder remains inside the radical. Okay? And if you don't want to do the division and you want to just write out your x's and circle your groups, that's totally fine. Alright, so let's see. 32x to the fourth. Let's break down the 32 first. So 32 is 2 times 16. And that's where I would stop, because I know the square root of 16 is going to make a 4 come out. But if you want to continue, that's 2 times 8, 2 times 4, and then 4 becomes 2 times 2. So I'm looking for pairs because it's a square root, and I have 2 of them. So I have a 2 and another 2 that are going to come out of that radical. And then, let's see, let's leave my radical alone for a second here. And I got a 2 and a 2 that will come out, and then I have a little leftover 2 that's going to stay in. Now for the variables, again, you could just divide, but you've got 4 x's in there. So if you're looking for pairs, that means 2 of those are going to come out. So you're going to have an x and an x that come out, and nothing left over in terms of variables. So now if we put all this together, final answer is going to be 2 times 2 is 4, x times x is x squared, and then a square root of 2. Okay, not so bad. Hopefully the color coordinating is helping, although it's making this tricky for me to write. Alright, let's try this again. So we're going to have a square root, let's see, 75. Does not divide by 2, it's not even, but 3 goes in 25 times. And then 25 we can break into 5 times 5, so there's my pair there. So I'm going to have my square root. Okay, and I know I'm going to bring out 2 5s, or sorry, a pair of 5s means a 1 5 comes out, and then I got this little leftover 3, so 3 is going to stay in. And then if I have x to the third, that's 3 x's, then a pair of those can come out and one of those stays in. So an x comes out and an x stays in. And I don't have anything to put together, so I can go ahead and leave that if I want, but just because I wrote it a little spaced out, 5x radical 3x is our answer. Okay? And this is bothering me, so let me put it a little closer together. Anyone else OCD issues like me? Sometimes I'm crazy about stuff, and sometimes I don't know. I guess sorry, you don't care. Okay, I think if you got a good handle on this, would be a good place for you to pause the video and try this out. Otherwise, let's see. 72 is 2 times 36. Again, that's where I would stop. I know that 36 is going to make a 6 come out of that radical, but if you want to keep going, that's 2 times 18, that's 2 times 9, and then that's 3 times 3, so you're going to be able to take out a 3, and you're going to be able to take out a 2, and you're going to have a 2 left. So when you go to simplify this radical, again, you're going to take out a 2, you're going to take out a 3, and you're going to have a 2 left. And then you've got 14 x's, okay? I would not divide or write out all 14 of those x's. This is one where I would take the 14 and divide by 2 and get exactly 7. So I'm going to have x to the 7th out here, okay? So let me just clean this up a little bit. The 2 times the 3 is going to make us 6, x to the 7th, and then our radical 2. Not so bad. Alright, got a couple more here. Let's see. Next one's a cube root. Same process now. We're just going to look for groups of 3. So 24 is 2 times 8. Just kidding. 2 times 12. And then 12 becomes 2 times 6. And then 6 becomes 2 times 3. So I've got a group of 2's that can come out. And then if I have 1, 2, 3, 4 x's, one of those can come out. So here's my radical, which is a cube root, so let's not lose the index, okay? We said we're going to take out a 2, and we're going to leave in a 3 for the numeric part. And then for the variable part, we can take out an x, and we have left over an x. So that is it. Our answer is going to be 2x cube root of 3x. Not so bad. Next, same thing, cube root, just got to be a little more careful. That negative is just going to make our answer negative, and then if we have a 3 that's already out there, we got to make sure that whatever we're bringing out is going to stay out. Okay, so let's see. If we break down the 135, that's going to be divisible by 3. 3 is going to go in 45 times. And then 45 is 3 times 15. And then 15 is 3 times 5. So I'm going to be able to take out a 3. And then I've got 6 x's. 1, 2, 3, 4, 5, 6. So 2 of those will come out, and I won't have any x's left over. So we've got our cube root. Okay. I had a 3 that was out there. That's got to stay out there. I've got a negative, okay, that's going to make my answer negative. And I said I'm bringing out a 3, and I have a 5 left over. And I'm going to bring out 2 x's and then no x's left over. So my final answer is going to be a negative 9x squared in front of the cube root of 5. Okay, organize the work. Shouldn't be too terrible of a process. All right, again, this is a good opportunity for you to try one out. Let's see, 343, I happen to know this one, is 7 times 49, and 49 is 7 times 7. If we've got x, that means it's a perfect cube. The cube root of 343 is exactly 7, so we won't have any numbers left over. But we have 1, 2, 3, 4, 5, 6, 7 x's, so 2 of those will come out and 1 will stay. So we have our cube root. Okay, we said we're going to bring out a 7 and no numbers left over inside. Then we were going to bring out 2 x's and we would have an x left inside. So this final answer is going to be 7x squared and then a cube root of x. Okay? So moving right along, hopefully, feeling all right with this. Let's see, we got a 4th root on the next one. Same process, now we're going to look for a group of 4. So 48 is 2 times 24, that's going to be 2 times 12, 12 is 2 times 6, and 6 is 2 times 3. So a 2 is going to come out and a 3 is going to stay. And then I've got an x squared, which is 2 x's. Now if I'm looking for a group of 4, I don't have one, which means I can't take any x's out. Alright, so let's look at our problem here. We got a negative, that's got to stay out there. Okay, so we've got a negative, and then our 4th root. Alright, we said we're going to take out a 2, and that we would have a 3 left inside, and that those 2 x's ungrouped, we're going to have to stay inside. So that's going to make our final answer negative 2 times the 4th root of 3x squared. Okay, again, that's a little far away. There you go. Be friends with the radical. Okay, let's try again. A 5th root. We're going to look for a group of 5 this time. And again, I know the 5th root of 32, but if you didn't, let's see, this is 2 times 16. That's 2 times 8. 8's 2 times 4, and then that becomes 2 times 2. Group of 5 means I can take out a group of 2's. And nothing's going to be left over in terms of numbers, and that's because 32 is a perfect 5th root. The 5th root of 32 is exactly 2. And x to the 10th, okay, again, this is one where I would just divide. 10 divided by 5 is 2, so I'm going to have an x squared coming out. And that's it, nothing left over, okay? This is an example of a perfect root. So like if I said, what's the square root of 4x squared? The square root of 4 is 2, the square root of x squared is x, and that would be it. It's exactly 2x, nothing left over. That's what's happening here, it's just maybe not as obvious. But I have, again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 2 of those, and nothing left over. Now, if you could look at that and know that that was what was going on, if you could recognize a 5th root of 32 is 2, and that 10 divided by 5 is going to be 2, so x squared will be left with nothing inside, and you could jump to the answer, that would be ideal, okay? But your answer is going to be 2, and x, and nothing left over. So this is exactly 2x. Okay? Alright, one left here for you to try. Let's see, this is 2 times 105, and then 105 is not even, but 3 goes in. 35 times, and then 35 is going to be 5 times 7. And then I have an x. So if it's a squared, I'm looking for pairs, but I don't have anything. I got no groups of anything, no pairs of anything. That means all of this stuff is stuck inside of the radical. So if nothing comes out, everything stays in, then this radical cannot be simplified. It is already in its simplified form, so it's going to have to stay as radical 210x. Okay? Hopefully that's not too bad. Again, just kind of a recap of what we did yesterday, throwing in the variable piece, but they work the same way, and feel free to use shortcuts where you can. Okay? Now, let's talk about something new, which it's possible you haven't seen before, but a rational exponent, and it seems like it doesn't connect to radicals, but it absolutely does. What does the word rational mean? Do you remember from our last module we were talking about rational expressions, rational equations, rational functions? Those were all fractions of polynomials, and the fact that they were fractions is what makes them rational. So a rational exponent is an exponent that is a fraction. Okay, so how do these things relate? Well, we can take something in a radical form and rewrite it in an equivalent rational exponential form, or vice versa. Something with a rational exponent can be rewritten in radical form, okay? And this really should make sense, especially based off what we just did, okay? What we just did was something like this problem right here. We said we could just divide that exponent of 6 by that index of 3 and say that this was going to be x squared, right? And even if it was odd, okay, if this was an x to the 7th here, we could still take that 7 and divide it by 3. Now, instead of rewriting this as a simplified radical, we could stay in this in-between stage and still have something that is equivalent. 6 over 3 is equivalent to 2. So this is exactly how these two connect. If we have the, let's say, the nth root of a to the mth power. Okay, if we have a radical, some index if we have the radical with any index, and then underneath the radical, if the radicand has a power, which it always does, if we don't see it, it's just a 1, that is equivalent to a to the, well, we take the exponent and divide by the index, so it's a to the mnth power. So we can take any radical and rewrite it as a rational exponent. Sometimes it'll divide, sometimes it won't. And then if the fraction reduces, that means that our radical and our index could reduce the same way. So we're just going to practice rewriting, not really doing any simplifying, just rewriting from one form to another. And to go from the radical form, this is our radical form, to rational exponential form. This is rational exponential form. All we have to do is divide our exponent by our index. Divide the exponent just like we did on the front, okay, by the index. So the fourth, even though this can be simplified, I'm not trying to simplify here, I just want you to practice rewriting, and then I'll show you how this is useful in a few minutes. This is equivalent to x to the 5/4. Okay, you take the exponent, divide it by the index. So those are the same. Equivalent, meaning it looks different, but it has the same value. Okay, so again, I'm not trying to simplify here, I'm just trying to rewrite. This is the same thing as x to the 6/3 power. Now I know it simplifies to 2 over 1 or just an x squared, but just for rewriting purposes, let's just keep it there. Okay. Now here, the index, we don't see it, but we know that there's an index of 2 there. This is a square root, so this is x to the 3/2. And then here we have a coefficient of 4 that's going to stay a coefficient, and then an exponent of 1. So we have 4 times, instead of the 5th root of x to the 1st, x to the 1/5 power. Okay. Now be careful on this guy. You might be tempted to say that this is equivalent to 9x to the 4/7. But then our answer would look pretty similar to what our answer was in number 4. But in number 4, the 4 was a coefficient. In number 5, the 9 is not a coefficient, but we made it a coefficient. Okay? In number 5, the 9 is underneath the radical. So think about this. Remember, Remember we said if we had the square root of 100, we could say that that's the square root of 25 times 4. Remember how we split this up so we could simplify? And then I could say 25 times 4 separately, because 5 times 2 would still get me the answer of 10. We can kind of think about this the same way, okay? We could separate this product of 9 and x to the 4th as a 7th root of 9 times a 7th root of x to the 4th. So really this should be 9 to the 1/7, because the power there is 1, multiplied by x to the 4/7. Okay? Now if you want to think about this another way, think about everything having an exponent, okay, and each of those being divided by 7. So 9 to the 1/7 x to the 4/7. In either case, okay, you have to make sure that the 9, because it's under the radical, gets that 7th root. Alright, and then one for you to try. So this is going to be 5x, the whole quantity is being squared, and it's under the cube root, so the whole quantity gets the 2/3 power. Okay? Hopefully not so bad. That's, again, just rewriting. Now let's practice going in reverse. Going in reverse is not as easy for some of us to see, but remember the bottom of the fraction, let me just go back here, the bottom of the fraction, that was the index, and the top of the fraction, that was the exponent. So when we go in reverse here, remember that the denominator of the fraction becomes the index, and the numerator becomes the power, becomes the exponent. So what I like to do is read these like from the bottom here and then around this way. So when I'm reading this, again, I'm going to read this as the square root of x to the 1st power. So read the bottom first, that is your square root. This is a cube root, this is a square root, this is a cube root, this is a 10th root, this is a 4th root. Okay, so let's read the denominator of the fraction first as the index. Okay, so here this is the same thing as the square root of x to the 1st power. Now I put the 2 and the 1 there just so you could see those numbers aren't disappearing, but we don't write an index of 2 just like we don't typically write an exponent of 1, so we're just going to make this a square root of x. Okay, here, and actually let me go back, this is kind of an important one because we see square roots a lot. We should really kind of implant into the memory that raising something to the 1/2 power and taking the square root of that something, those are equivalent operations. The square root and the 1/2 power are the same. So the square root and the 1/2 power, just like a cube root and a 1/3 power, or a 4th root and a 1/4 power, they're all equivalent. So they're good things to implant into the memory. Okay? Alright, how about this guy? Let's see, we have x to the 9/2. That is, again, a square root of x to the 9th. So square root of x to the 9th. And then this would be a 10th root of x to the 3rd. And again, make sure you're writing the index smaller and kind of tucked into the radical. We don't want this because it looks like 10 times a square root. We want a 10th root. Okay? Let's see here. Be careful. The 2/3 power only applies to the x. It does not apply to the 2. If it was a 2x like this with a 2/3 power, then the entire quantity is going to go, oh, that's the next one. The entire quantity would go underneath the radical. But here, the 2 is a coefficient. It's going to stay a coefficient. And then I have a cube root of x squared. 2 times a cube root of x squared instead of 2 times x to the 2/3 power. Okay, now here again the whole quantity is being raised to the 2/3, so this is going to be the cube root of the whole quantity squared. So the cube root of the whole quantity squared. And if you did not put the parentheses here, that would change the answer as well, because now the square only applies to the x, and we wanted to make sure that it applies to the 2 as well. So make sure that quantity stays together. Okay, last one. Be careful. This is just like number 9 there, where the 2 is a coefficient, the -1 is a coefficient. So this is like a -1 times x to the -3/4. So we want to make this a -1 times a 4th root of x to the 3rd. So 4th root of x to the 3rd. Okay, so rewriting. And part of the reason why it's helpful to be able to rewrite, well, we saw the dividing the exponent by the index was helpful in simplifying, right? We already saw that on the front, but this is also helpful in evaluating some things that look a little strange, like 125 to the 2/3 power. I don't know if you've ever seen anything like that before, but if we were to rewrite it in radical form, then it'll make a little more sense. So we're going to rewrite these in radical form and to evaluate, and then we're going to use Desmos. We're going to use our calculator to verify. That's not what I wanted there. We're going to verify with the calculator, which is our Desmos. Okay, so 125 to the 2/3. Again, this is the cube root of 125 squared. So this is the cube root of 125 squared. So even though I had no concept of what, maybe you don't have a concept of what it means when you're looking at it as 125 to the 2/3, this you should have a little more of a feel for, because cube root of 125 should look familiar. Now, we technically don't have the option of going in either order. Like, we could take the cube root first and then square, or we could square first and then take the cube root. The order that we're handling these things don't really matter because they're both considered an exponent. So exponents, yeah, whatever order you want to work on them here. So what do you think would be easier? Do you think it'd be better to square the 125 to make a really huge number and then take the cube root? Or take the cube root to make a really smaller number and then square? Yeah, I said it like that on purpose. Let's take the cube root first. So the cube root of 125 is going to be 5, and then we can square, and 5 squared is 25. So this thing is equal to, this expression is equal to 25. And again, this could be confirmed with the calculator. So if we put in 125 and we hit the AB button, we give ourselves a power of 2/3. It's going to tell us the same thing we just got, which was 25. So the hope is that you can evaluate these without a calculator, but by all means use it to verify what you're doing. All right, so here, this is a negative coefficient, so this is a negative, and then a square root of 121 cubed. A square root of 121 cubed. Again, we're going to make this, or take the square root first and then cube. So this is a negative. The square root of 121 is 11, and then 11 gets cubed. So that's going to be a negative 1,331. That I just happen to know off the top of my head. It's ridiculous. There's lots of ridiculous information in my head, just so you know. Okay, 121. Let's raise it to the 3/2 to confirm, and there it is, negative 1,331. Okay, how about this guy? This is probably this would probably be one of the tougher ones to evaluate without a calculator if you don't remember exponent rules. Remember anything about negative exponents? Okay, maybe not. So let's put this in the calculator first. If we had 16 to the negative 1/4, 16 raised to the negative 1/4. We get a decimal, or we get a fraction of 1/2. Why does that happen? So a negative exponent, geez, how much do I want to get into this with you? If you have a negative exponent, it just means that the base of the exponent is on the wrong side of the fraction. So like, okay, if you remember anything about exponent rules, if you had, let's say, x to the 3rd over x, or x to the 5th over x to the 3rd, we could simplify by subtracting these and saying that's x squared. And the reason we can subtract is because if we have 1, 2, 3, 4, 5 x's on the top, and then 1, 2, 3 on the bottom, that 3 of those would just cancel and leave us with the x squared. Okay? If we did it in reverse, if we flipped that fraction, if it was x to the 3rd over x to the 5th, we could still subtract, but it would be a negative 2 this time. And that negative 2 is telling me that those x's, they don't belong in the top of the fraction where I put them. They belong in the bottom. Because you have 3 x's on the top, you have 1, 2, 3, 4, 5 on the bottom. 3 of them still cancel, but where are the 2 that are left over? They're on the bottom. So really this should be 1 over x to the positive 2. So anytime you see a base with a negative exponent, that's just telling you that that base is on the wrong side of the fraction. So going back, going back here, This is telling me the 16 doesn't belong on the top of the fraction. That's where it is right now. It's on the top of the fraction. It doesn't belong there, it belongs on the bottom. So we're going to rewrite this as 1 over 16 to the positive 1/4. And then we're going to evaluate from there. So this is 1 over the 4th root of 16 to the first. And the 4th root of 16 is 2, which is why this ended up being 1 over 2. Okay, definitely trickier than some of the others, but again, could be verified or even just input into the calculator. All right, let's try this guy. This is a 5th root of 32 cubed. 5th root of 32 is 2, and then we cube the 2, which makes 8. Okay, 1/2 power here. Remember what the 1/2 power is? That's just a square root. So this is a negative square root of 25 over 121. So square root of 25 is 5, square root of 121 is 11, so this is a negative 5 over 11. And then here, that's a negative coefficient. A negative times 27 to the 2/3, which is the same as a negative times the cube root of 27 squared. So a negative times the cube root of 27 is 3, and 3 squared is 9. So this is a negative 9. Again, all could be confirmed with the calculator, okay? So 2 reasons why it's good for us to be able to go from rational exponents to radicals well, they work in both directions. If we have a rational exponent, we can use the concept to evaluate, and if we have a radical, we can convert to a rational exponent so that we can try to simplify that radical. So we saw that on the front. All right, so hopefully that wasn't too bad. You've got some practice to work on, so try to knock those out, and as always, if you get stuck, then just reach out. All right.